Well, thank you for coming. So this is, as you can see, a talk about delivery pipelines. Does it work over here? This mic works, not just that mic? Good, cool. Because I like to walk around. My name is Farrell. I'm a Red Hatter. Been working on OpenDaylight for a long time. This talk is going to be really laid back and informal, so you're welcome to interrupt at any time and ask questions at any point. We should have plenty of time. I just tweeted out a link to these slides, so you're welcome to take photos to document things if you want, but you also don't have to. My username is dfarrell7 everywhere, so if you find that on Twitter, you can find me. Super quick background about me and why I'm giving this talk. Again, I'm a Red Hatter. The relevant part is this first line. The integration packaging project of OpenDaylight is responsible for basically everything you're going to see today. So delivery pipelines, starting from packages to config management to pre-built images and all the consumers and sort of interfacing with downstream projects and things like that. I also work with OPNFV in the CPERF project. Cheers to Al and my other CPERF people in the room. I'm a committer to integration tests and some CentOS things, and I do some governance things for OpenDaylight. So quick overview of OpenDaylight's continuous delivery pipeline. And by continuous delivery, we need as fast as we can, but making progress in that space. So I like to talk about it in terms of a three-layer stack that I've kind of made up. This is not some sort of OSI-approved three-layer stack that you'll read about in textbooks, but I think it makes sense for describing the abstractions that we care about here. So the first layer is the packaging layer, and we'll talk about all these in more detail. At the packaging layer, we have things like the RPM and the deb package from OpenDaylight. Second layer is config management layer, so that consumes the packaging layer and builds on that. At the config management layer, we have options like a OpenDaylight Puppet role, OpenDaylight Ansible role, Puppet module Ansible role. Other third parties have things that we're kind of working on upstreaming more, like Juju Charms, for example. And then the final third layer, we have what I call pre-configured images. So these are things like Vagrant base boxes or Docker containers that are built using tools like Packer. And again, these are consumed, each of these layers consume the previous layers. So these are built using tools like Ansible, which in turn use tools like our RPM and deb. So let's break out these layers and talk about them in some more detail. So the package layer, what do I mean when I say that? I think that the package layer does things like handle files, lay down the files in the file system in the right locations. I'm talking to the wrong slide, sorry. It also handles system level dependencies, which in OpenDaylight's case is Java. It lays down the files. Once we have files, and we can go ahead and create the required users and groups, and once we have users and groups and files, we can set permissions. Does things like manage OpenDaylight using systemd, so put the right magic files in the right locations so that we can do sudo system control start OpenDaylight and stop OpenDaylight and restart OpenDaylight and help manage that with other tools. For a long time we've had RPMs, and those are being consumed by all kinds of downstreams, including OPNFV installers and such. Just recently we've added debs, so in the room somewhere we have our deb intern. So big shout out hero to the room, yay, thank you. Okay, and all the OpenDaylight interns, by the way, have done great this semester, so, or I don't know, summer or something, so if you see them in the halls, give them a pat on the back and tell them thank you. Okay, so RPMs, talking about sort of a specific instance of the packaging layer, and normally we'll go with what came around temporally first, so we'll start with RPMs. They're all the source for building RPMs. I guess I should explain that. Everything that involves the building of an RPM is stored in version control, so it's a bunch of scripts and that contain sort of the rote logic and then a set of YAML files that contain the changing part, the data part. So you write a new build definition in YAML, you input that into build scripts, and you get an RPM out via the super automated, totally in version control process. So you can go look around at how to do that in the integration packaging repository, and there's decent docs there. We also have a job, Jenkins job, that builds RPMs. So this is a screenshot of some built RPMs here, but if you were to go look at the parameters section there, there's on the left, there's a set of places, set of fields that you basically define everything relevant to the RPM. So what version of OpenDaylight you want to build and the different types of the version numbers, major, minor, package, things like that. What systemd file to install, all the parameters involved in creating an RPM, you yourself can push into that parameters field and then have this nice magic output stored in ODLâ Jenkins forever. We also, so that's sort of one place that we build and host RPMs. We then I typically download the RPM from there and then push it to the CentOS community build system. for sort of longer term hosting and typically faster downloads. Our infrastructure people chuckle at that. So here's Boron, for example, on the CentOS community build system. Every build we've ever done is here, so you can go look at sort of the permanent log of everything relevant to OpenDaylight RPM-wise. Let's see an example of how to install the RPM. And it's going to be nice and easy, and our examples are just going to get easier as we go, so feel not overwhelmed. This is a directory in the integration packaging, subdirectory RPM, subdirectory example repo configs. It's just a bunch of .repo files that we provide for people as sort of examples, obviously, to install RPMs from. So we recommend these. These are kind of the de facto standard for how you should be consuming our RPM repositories. They're really simple. The important line here is this little laser. Yes. How do I use it?
The blue button, black button in the middle.
There we go. The important line is the base URL part here. And this is just saying where to find our RPM repositories. The .repo file is just a configuration thing that says, here's how you find our RPM, since they're not available in EPAL or the sort of big repositories yet. Once you have this file, so you'll pick the file you want. The 5.0 release is what we're using now for Boron. You curl that down to your local file system in etc yum repos d, OpenDaylight, and it happens to land with the right permissions. So once that's down, we can just do sudo yum install -y OpenDaylight, and boom, we have our package installed, systemd configured, permissions set, users configured, all of that good stuff. We then can just do system control, start OpenDaylight to spin up ODL's process, and we can verify it's active with little helpers like is active. We can grab our carafe shell using, say, for example, the client executable, and then do our magic like feature installs or whatever else we need to do with OpenDaylight. So let's into that example. I'll call out in the future, we are moving towards, this whole process has been moving towards some better, more automated delivery pipelines, right? So for the beginning, everything was super manual and slow. It's gotten more automated, more things in build systems, continuing to speed up as we have cycles to automate things. The next steps there are probably going to be mostly copying Fido. So I have a good relationship with Ed, and he's been showing me kind of what they're doing in the Fido community around packaging. And they have some pretty good reusable reusable chunks of logic that I think we can just copy basically and get excuse me, RPMs and probably debs building in our build system pretty quickly, and for every single auto release build is the objective. Excuse me. All right, so a little bit about the deb. It's in the same integration packaging repository in the subdirectory deb, go figure. It has decent docs, and it's all automated in the same way around, there's a set of sort of changing logic that's defined in YAML and a set of build scripts and templates that are static. So with a few parameters, you can define new debs. It's hosted on the OpenSUSE build system. I think I meant to give there's another screenshot here that is more beautiful and has some links about how to download it and stuff, but I think if you follow that downloads package link, you can find it. But that's very new. This is, I don't know, a week old or something that we've got it up here. So I guess announcing for the first time, you can go pull down our deb package from this location. All right, so that's it for the package layer. Layer 2 of our made-up OSI model is the config management layer.
Water.
Thanks, man. JMO always watching out for me. So config management layer, what do I mean when I say that? So it consumes ODL via the packaging layer. We're trying to be good software engineers and get some reuse and building abstractions. That's kind of all we have in software engineering as far as good habits. So I guess the main responsibility of the config management layer is it edits files to apply configuration, as the name would imply. So the main ones that we care about in OpenDaylight's use case is the carafe features that are installed at boot. Everybody has to edit that one. Also port mapping, which you typically have to edit to make it not conflict with like OpenStack Swift, for example, and configuring or disabling L3, setting various log levels, deploying in HA or not. Shout out to OPNFV for driving all of those knobs basically as they do real deployments and need things that can be configured. That was almost all driven by OPNFV. Other things, opening ports in firewall D, managing systemd service, starting, stopping, restarting. So first instance, again, moving temporally with what came around first. First instance of a configuration management tool that we built uses Puppet. We did that mostly because OpenStack uses Puppet, and that was a big driver in the community and the ecosystem at the time. So we wanted to sort of make it easier for them to interop with us. I would not build it in Puppet again. So, fair warning, it's very easy to consume, both the Ansible role and the Puppet module from a user perspective. We'll see in a second, they both have a very similar API to a user, but if you ever need to dig into one of the two to like make changes to the configuration management thing itself, you have tens of thousands of lines of domain-specific languages in Puppet, or you have YAML configurations in Ansible. So I highly recommend a few hundred lines of Ansible YAML configurations versus thousands and thousands of lines of weird domain-specific languages in Puppet. So this is, for now, unfortunately, this is hosted under my GitHub, dfrail07 Puppet OpenDaylight. Andy maybe is in the room. Has just told me in the hallway that he's signed a contract to get ODL Forge infrastructure bumps. So we're actually going to have our ODL Forge after years and years and years of talking about it. And so when we have that, hopefully this will be one of the first projects that we migrate to be on sort of official infrastructure, but consider it an official project even though it's on my GitHub. It's submoduled under integration packaging, so it's official in that sense. It's also available for download via the Puppet Forge, so automated tools can find it if you use Puppet automated tools. It has a very well-developed API. Again, we can thank OPNFV for this, because they just continue requesting knobs in different ways that they configure things, so each of these tags is an API change. Again, because we have a fair number of consumers of the Puppet module, there's good docs, so let's take a scroll through some contributing docs. We have how to communicate, how to raise issues, how to send patches, how to run syntax and style tests and unit tests and system tests and all kinds of good things. This is flaking out of me. Okay, so we have, I guess, the widest operating system support in the Puppet module. This needs a little bit of an update, just some version bumps to newer versions of Ubuntu and Fedora and stuff. But even before we had our deb package, we were able to support Ubuntu-based installs with the Puppet module, because we have, also I should say, that the Ubuntu support came from the community, so shout out to David from Orange for that pull request and the various other contributions associated with it. Thank you. So before we had debs, we could also do tarball-based installs in the Puppet module, but they're very complicated. So we're soon going to rip out all of this logic and replace it with simple package management logic using debs. But how we did that is by just providing a link to a tarball and a link to a unit file, systemd unit file, and then we did basically everything that the RPM does manually in the Puppet module with Puppet logic, and that's just way more complicated than it needs to be. So looking forward to removing that code soon. The Puppet module is really well tested. There's all kinds of different types of tests in Puppet world. The first one is called RSpec Puppet. It's like unit tests basically for Puppet. It's not so, it's debatably a good idea because it basically just sort of doubles what you wrote in Puppet. It's like you write your actual Puppet logic and then you write exactly the same logic in the form of a test case. And so if you make any changes, you have to update both. And like it's sort of helpful for quick syntax checks and things like that, but overall not the most helpful testing framework relative to how much work it takes to put into it. So we won't talk about it in too much detail. We will talk about one that I enjoy a lot called Beaker, which makes my life a lot easier. Beaker is nice because it's more realistic. It stands up real virtual machines or containers using Vagrant or Docker, and then deploys using the Puppet module, OpenDaylight, on these VMs, and then looks at the resulting state of the VM and verifies things. And repeats that for the config knobs that we talk about, that tweaks you can make to using config management tools during the OpenDaylight install. It does that for various combinations of config knobs, and repeats and checks and repeats and checks. So, I should say. So when I say at a high level like this, I'm going to show you more information than you can take in, but then I will go back and show you sort of the detailed part that I care about. This is so you can see the flow of things, the color, the general amount of output and such. So at a high level, be overwhelmed. This is what a Beaker test looks like. So just tons of actions and checks scrolling by. Each one of those green ones is a verification of some state of the system. I think that was sped up. It takes longer than that in real time. So in detail, extracting a few relevant parts, we do things like start up a CentOS 7 virtual machine using VirtualBox or libvirt or whatever. We have to install Puppet on it, then we repeatedly apply our test manifest. So that's what has these parameter combinations. We then do checks like whether OpenDaylight is running as a systemd service, whether certain groups and users are configured, whether files match certain regexes, which in this case is important because it means certain features should be installed. And there's some number, 132 checks at the time of writing of tests like that. So Beaker's pretty great. As a module maintainer, I have a lot of confidence that when someone sends us a pull request and we can run the Beaker test successfully, that if I merge this, I'm not about to break OPNFV, because it does get pulled down directly into OPNFV. So we would break OPNFV if we broke the Puppet module. So let's walk through another example. This time we'll use a Vagrant provisioner to, so I'll quick detour to explain Vagrant for a second. Vagrant is a tool for managing virtual machines. It has different types of provisioners that do the configuration. So the most basic one is the shell provisioner that just runs shell commands against the virtual machine, and you can standardize and keep on a certain Vagrant file these shell commands that can be shared in version control. There are other provisioners that are more complicated, like the Puppet provisioner, the Ansible provisioner, are ones we're going to demo today. And so they use Puppet modules or Ansible roles to do the configuration. And again, it's all stored in version control and easy to share. You don't have to share binary VM blobs with people. You just share the configuration of how it should be built. So Vagrant's really nice. So let's see an example. I should say that this repository is where all the Vagrant examples are coming from, by the way. It's under my GitHub again, but d7, Vagrant, OpenDaylight. Think of it as a matrix of different deployment options to operating systems, and you can play around with every deployment option in every operating system, basically. So at a high level, again, more information than you can take in. This is what a Vagrant box definition looks like. Oh, there we go. So most of this is comments, but it's still pretty short overall. Basically, the important part is at the bottom there, where we're saying what Puppet manifest file we want to look at. So this install puppet.pp file is the important part. It breaks out into this. So again, super simple. All this is saying is apply the class OpenDaylight, override the extra features parameter with this. It's empty by default. With this list of one extra feature, which is ODLâ network OpenStack, which is the one that you would install typically to do network virtualization with OpenStack, like in OPNFV use case. We then provision the box with a simple Vagrant up, name of box, and then we get this output telling us what's going on. So we're curling down our Yum repository to have that .repo file I talked about how to find the RPM. We're then installing the RPM from that repository. We modify the magic files to install certain craft features at boot. Let's grab a shell in our box and poke around a bit. So we can use Vagrant SSH name a box, and now we have a shell on this new virtual machine. We can sanity check that ODL is running, the system control is active, and of course it is, because this is a demo and not even running. Yeah, then we can connect using SSH as an example, get our OpenDaylight craft shell, and then use this feature list as, I'm trying to teach you commands as well as we go. We can use feature list and grep against that to verify that our feature was installed. So ODLâ network OpenStack, which is the one we told Puppet to install, is in fact installed, as you can tell by that X that means it's installed. This is boron in this example. So that's Puppet. Ansible came around second. Again, both interfaces from your users, pretty simple, but if you ever need to modify anything, definitely recommend taking it the Ansible route. So it's in the same realm of projects that need to be in their own repositories. I didn't say that with Puppet. The reason we have it in its own repository is because these tools prefer to live in their own Git repositories. They really need to have their own tags. They can't share a repository with other tools. So it's in its own repository under my GitHub, soon to move to Puppet Forge, ODL Forge, sorry. It's in Ansible Galaxy, so automated tools can find it. The Ansible role is quite simple, as I said. It has basically this is kind of its heart, this task main.yaml, which breaks out into a few other simple tasks. Those aren't so big themselves, so this one's responsible for managing ODL system D service. Again, as you can see, it's just a few lines of YAML configuration. This is probably the most complicated one, and it's not very complicated. This one is responsible for modifying that magic file that sets certain craft features to be installed at boot, also dealing with the permissions and ownership of that file, also has handlers for doing restarts of OpenDaylight to make sure that when we remove features from that file that you have to do a restart to make them actually be removed. So lots of work being done by this simple YAML file. Overall, there's about 200 lines of YAML configuration, so it takes maybe 10 minutes to read through and understand what's going on. One reason it's so simple is because Ansible rejects Puppet style of testing. These are direct quotes from the documentation. Don't test your playbooks. Pretty straightforward. Ansible believes you should not need another framework to validate basic things of your infrastructure. Kind of a jab at Puppet, I think. But it works really well for them. So there's no RSpec Puppet or Beaker level testing. They really kind of focus a lot on failing fast and cleanly and making the failure really obvious to the developer. So you can just, your test is kind of your deployment against a VM, and then maybe you'd run like robot test against the result or something. But instead of having this tooling to help you detect failures, they just, in the failure message, it's not so incredibly obtuse like Puppet, and so you don't need so much help to figure out what went wrong. That allows developers to focus on the deployment logic, and it seems to work pretty well. So let's see an example. This one's parallel to the one we did with Vagrant. So again, we're using the same Vagrant OpenDaylight project. This time we're going to use the Ansible provisioner. Also, the word provider is an important thing in Vagrant world, but we can ignore that. So at a high level, again, more information that you can take in. This one's even simpler and more docs. The relevant line is at the bottom. We're saying, use the Ansible provisioner and use this particular playbook. So it's provisioning playbook.yaml. Again, super simple. It's saying apply as root, apply the role, open daylight, and accept all the defaults. So this time we're accepting all the defaults. Let's go ahead and provision the box. Again, with Vagrant up, name a box, and we'll see this type of output. I want you to look at the colors here because it's kindergarten and colors are fun. But really, the importance of the colors is they show you what changed. So the yellow ones means that things changed about the system. The green ones means that nothing needed to change. The blue ones mean that the state of the system was such that those steps shouldn't run, so they didn't run. So you notice that there were a lot of yellow things. We changed a lot of things. So things that we changed included installing OpenDaylight via the Yum repository, opening some ports, starting OpenDaylight systemd service. Let's grab a shell in the box and poke around. So Vagrant SSH name of the box again. We can sanity check that ODLâ is running with system control is active. So before we get too far into that, remember that we didn't set any features to be installed. Let's go back and do an update of this box using the Ansible provisioner. So we've modified our playbook file to override again this extra features list with the same demo feature we did before. This time we'll use Vagrant provision name of box and we'll sort of rebuild that box, but it does it pretty quickly. Notice that this time there's very little yellow. There's just that the one yellow thing and then some handlers that were kicked off. So the yellow one was what we would expect around modifying the craft features that are set to be installed at boot, because that's what we said, install this feature. And then we kicked off a number of handlers to make sure that that takes effect. So we can grab a shell and sanity check that ODLâ didn't break during that whole process. We can then, this time we're using a connect.sh helper script to SSHN, but I'm just showing different ways you can connect to ODLâ. We get our ODLâ shell, and then we check that our demo feature is installed, and according to RX, it is installed. Okay, so final part of the stack. How am I doing on time? I don't even have my phone up here. Can somebody look at that and tell me? What time am I supposed to end? I'm over. All right, so we'll be real fast. This is the ending anyway. It's a quick end. The pre-configured images, they're OpenDaylight already installed using the tools we talked about in the past. We're just being good software engineers and trying to reuse past ones. They're Vagrant-based boxes and Docker containers. They're built using a tool called Packer. Packer is cool. Everything's in version control, and it builds our Vagrant-based boxes. Here's the version control thing. It lives under integration packaging, as everything else has so far. We talked about that. It uses Ansible, so when we make Ansible updates, we get those for free in Packer. Container demo, this is the quickest and most beautiful OpenDaylight demo that I have for you. I call it the one-liner carafe shell. So with this one line of magic, you can download OpenDaylight Boron 5.0 and Docker container and start the carafe shell. So this is what the output is. It handles all the download and everything, and you're magically running OpenDaylight, which you can verify with Docker PS. So that's a short example because it's so easy. Vagrant Basebox, also super easy. Maybe the best user experience because people are familiar with VMs. Super simple example is this. All you have to do is the first line creates the second file here that I'm catting out. The only important part is that we're starting with the box OpenDaylight ODL and accepting the default version. We can then Vagrant up that box, handles the download from Atlas. Our VM is running, we can connect, and ODL is already running. We didn't have to build it, we didn't have to start it, it's already just working. Conclusions, OpenDaylight has many deployment options. You should use upstream options instead of building your own. If you are building your own, come work with us and we'll make sure we have the features you need, basically, and try to support you. And contributions welcome. Here's all of my contact info, and thank you for your time.